Hello students, today I will take up the topic which is relevant to general purpose input output programming. As you can see the kit here, through input output programming, our aim is to control general purpose LEDs. Here on my left side, on the left side of your screen, you can notice the general purpose LEDs. So here these LEDs, you can see these LEDs. These are 8 in number in our kit LPC1768. In this kit these are 8 in numbers. These LEDs we want to control using our code, and as you know, the system code, this microcontroller, has 100 pins. Out of 100 pins, 70 pins we can configure as general purpose input output pins. Those input output pins can only be used for controlling the peripherals. So here this journal LEDs are our peripheral, and our aim is to control these peripheral unit. And how to control it? Sometimes we want to blink the LED, sometimes we want to switch off the LEDs. So sometimes we want a certain pattern through which LEDs should go on and then go off. So in this way we want to control our LEDs. How you can do it? Obviously you have to connect your LEDs with our system code. So for that purpose, we will use the port number 0 and pin number 4 to 11, because we require 8 pins, because 8 LEDs are there corresponding to individual LEDs, individual pin we require out of that port. So port number 0, pin number 4 to 11 we will use. Now how to actually know that which pin we will use and how we will connect later on? For that purpose you have to look back and go to your appendix C in lab manual. So here you can see the GPIO extension connectors. So those are 4 in numbers, C and A. So here as you can see, this is C and A encircled, this is C and A, this is C and B, C and C, C and D. So these are the connectors which offer the connection, which connect the port pins with the outside peripherals. So if we want to use port number 0, pin number 4 to 11, how we have decided it? So if you will see that C and A, this connector provides the connectivity of port number 0, pin number 4 till pin number 11. 2 pins. So these connectors, these are male connectors. Total 10 pins are there in individual connectors. DNA has 10 output pins. So output connectors 10 in numbers. Out of that, only 8 are corresponding to port pins. 2 are for power supply purpose. 1 is for grounding purpose, and 9th one will be for no use. So our aim is here to use port number 0, pin number 4 till pin number 11. Likewise, if you want to use some other port, some other pin, so here you have to always consult this appendix C. It is not with your whims and fancies you can use any port and any pin, because then you will not be able to properly connect that port and its individual pin to the outside peripheral. So first, corresponding to every connection to make, you have to understand that if the port and pin is fixed, where from it will get the connectivity to its port. So C and B will provide provide connectivity to port number 1, pin number 23rd, 24, 25, 26, and port number 2, pin number 10, 11, 12, and 13. Likewise, C and C will provide connectivity for the port number 0, pin number 15, 16, 17, 18, 19, 20, 21, 22, and port number 2, pin number 13. Likewise, C and D provides the port number 0, pin number 23rd, 24, 25, 26, 27, 28, and port number 2 and its 0th and 1st pin. So there always, whenever you start with any program and you want to think about connections, that how to actually connect the outside peripheral with system. So you have 4 connectors. Out of those 4 connectors, the first function, every connector, every port pin, first function is GPIO function. So here, every port, every pin, you will not be able to connect through your through these connector pins. So which pin to use, here you always consult the appendix C. So here, after consulting the appendix C, we confirm that about the use of port number 0, pin number 4 to 11. So port number 0, pin number 4 to 11 comprises of total 8 pins. So those 8 pins, individual pins, should be for individual LEDs. And we want to then control those LEDs through those 8 pins of port number 0. Then we will go ahead. So in this way, so here we have to connect this LED connector with C and A. If you will use some other port pins, other port and other pin corresponding to whether you will get the connectivity out of C and B, C and C, C and D, you have to decide based on appendix C. Now, once you are with your connection ready, so everything is all right, then we will start writing C program to actually coordinate our task. Our task here is to blink LEDs in certain patterns. We want to control the LEDs blink in certain order. So for that purpose, we will go through the programs to understand that how we actually control it. For that purpose, we have to write the C code, and here you can see the PEEL software. So in the PEEL software, today we'll understand several programs. We'll start with the basics. The basic program is you have had 8 LEDs in number. We want to represent the Johnson counter over those LEDs. So we want a Johnson pattern, Johnson counter pattern over that LED. So what is the Johnson counter? Johnson counter is that if you will number the LEDs from left side to right side, 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7. So that's the numbering which I have mentioned, and later on I will stick to this numbering. So here our aim is that first we will blink 0th one, then in the next move we'll keep the 0th as it is, and then we will switch on the next LED, then we will switch on the next LED, then we will switch on the next LED. In this way we will go till the 7th LED, and then we will start switching off the LEDs from the 0th number. We will switch off the LED 0, we will switch, then later on we will switch off the LED first, second, third, fourth, fifth, sixth, and then we will keep on repeating this cycle. That is the Johnson counter and its representation over LEDs. So individual LEDs you can correspond to individual bit. So if the Johnson counter in bit form you have to understand, then 0th bit corresponds to the 0th position LED. First bit corresponds to the first bit LED. Likewise, the 7th bit corresponds to the 7th position LED. Now, corresponding to these LEDs, we have already connected these LEDs with 8 pins. those pins corresponds to port number 0, pin number 4 to 11. So port number 0, pin number 4 corresponds to the bit position 0 or the LED position 0 if you will look into the LED modules. Likewise, port number 0, pin number 5 corresponds to the second position and so on. So this is the program which we have to realize. Now we will write the C code. So obviously for that purpose we require to include lpc17xx.h. As we have understood in our last lecture that the GPIO, the general purpose input output, any port. So port is a logical construct. We have total 5 in numbers, and so inside port we have pins 32 in number. Out of 32, some are reserved, some we will use. So as here in this case, we want to use port number 0 and it's pin 4 to 11. So first task is to actually configure those port pins as GPIO pins. So this is the by default function. Why is it by default? Because to configure any port corresponding pin with a specific function, because individual pin can function in 4 ways. So here the first function we want to realize through configuration. So we will go inside the structure LPC pin configuration. Here you can see LPC pin configuration. So this structure definition is there in lpc17xx.h. So once you dereference this structure, there is one register. So that register is pin select 0 register. Pin select 0 register, these are total 11 in numbers. Out of 11, first 10 we will use for configuring the function corresponding to that pin. So here by default it is 0. Even if you will not write this statement, by default all pins are configured as GPIO pins. But here explicitly to actually show how to do it, here from pin number 4 to 11, we have explicitly made the positions corresponding to those pins in pin select 0 registers as 0. So if you will take this and go to calculator, and here if you will write and then see the binary of it. So here is the hexadecimal and the binary of it. So from position number, this is initial 4, next 4, and pin number 4. So in pin select register 4 to the 8, from 8th position till 11, 11 to the 22, till 22nd position everything is 0 0. So 2 0 zeros, these 2 0 zeros corresponding to port number 0, pin number 4. Configuring that port number 0, pin number 4 as GPIO, it should be 0 0. Likewise for 5th pin, here, next 6th pin, 7th pin, 8th pin, 9th pin, 10th pin, and 11th pin. Other things are 0. So that's how you can configure explicitly, even though if you will not do it, or if you will not even mention this statement here, it will not make any difference, because by default the pin select 0 holds all 0 values. So by default everything at the very outset configured as general purpose input output. Then once you have configured it, the next task is to set the directions, because these pins are there. System has already understood that these pins are going to be used as GPIO pins. The next task is that whether these pins will be used as input pins or output pins. So here our aim is to configure those pins as output pins, because from there our LED module would take that output as input to the LEDs. So from system point, from the core point, if you would see, then these pins, system would write values over those pins. Core would write values over those pins. So that's why we have to configure those pins as output pins. So to configure those output pins, obviously we have to use the FIO direction registers. The total 5 registers are there to actually manage any port. So first is the direction, you will set the direction. Then if you want to read the value over those pins, then FIO pin register is there. Even to write to FIO pin can be used. Then to set any individual pin as high, we have FIO set register there corresponding to that pin bit position. We will write the value 1, and if you want to clear it, means if you want to bring 0 over that pin, then corresponding to that pin position in FIO clear register, we will write the value 1. And FIO mask, already we have discussed. So these are 5 registers which have been used to handle the GPIO efficiently. Now direction being set, that is all over. So already we have set the direction, we've configured those pins as GPIO pin, system has already understood direction, configuration, everything is all set. Now we want to realize Johnson counter. So Johnson counter is what the first LED should go on first, then it should be on, and then in the next move second, then in the next third, fourth, fifth, sixth, seventh. Likewise, then in the next cycle, everything you have to clear. So we will see the Johnson Johnson counter first. So here is the code for Johnson counter. So first we have configured pin select 0 register, direction being set. So here in the infinite loop, once we come inside the infinite loop, then we are using one LED variable. So here this LED variable, so fourth position of this LED variable is 1, because first time what we actually want to do, first time we want to switch on the first LED, but the position is the fourth corresponding to the port number. So port number 0, pin number 4 is connected to the first position in the 0th position. So here you can see the fourth one is 1. It is in hexadecimal. If you will convert this hexadecimal into its equivalent binary, then you realize that the 1 here corresponds to the 4th bit position. Means we are counting it from the 0th bit position, 0, 1, 2, 3, all zeros, and the 4th bit position is 1. That is connected to, because port number 0, pin number 4 is connected to the 0th position of LED, the 0th LED that we initially want to switch on. So here we go inside one loop, because 8 times we have to do the operation. So 8 LEDs are totally numbers. So 8 LEDs one by one we want to switch on. So how we can do it? So first time our LED is equal to 4th bit position is 1. Next time when you will go inside the loop, next time, because first time when you will go, so what actually are we doing here? We are actually setting FIO set. So FIO set register means pin number 0, port number 0, pin number 4 we want to set as 1. So that's why it is equal to LED. That means that pin means port number 0, pin number 4 will go as 1, and that is connected to LED 0. That is connected to LED 0, and henceforth after the statement that LED will glow. Then we will introduce certain delay. After that delay, so nothing we are doing in this loop. So we are introducing some random delay for a while, because we want to see that it means we want to realize that the LED is on or not. So once it's been realized after this gap, after this delay, then we are changing the value of LED. Now we are shifting LED by 1. So we are shifting it by 1. That means initially the fourth position was 1. Now in the next move, fifth position will be 1. And the fifth pin, port number 0, pin number 5th, is connected to the first LED position. Previously, LED was means in LED fourth bit position was 1, and at that time fourth position is connected to the 0th position in LED module. And the second subsequent move, we are left shifting the LED. After you shift it by 1, then 1 will come on the fifth position, and that is connected to the first LED position. Second time it is connected to the third position. Fourth time it is connected to the fifth position. Likewise, uh, in 8 cycles in this loop, in 8 cycles, at the last move, when I is equal to 8, at that time the 8th LED will glow. Now, so that one cycle is over. Now exactly in the same way we will clear it, because that is what the Johnson counter is. Initially you will switch on all the LEDs one by one, and then in the next move we want to switch off all the LEDs one by one. So what we have to do, exactly the same loop structure we will use instead of FIO set. This time instead of FIO set we will use FIO clear, because at that time we don't want it to set as I1. We want to make it clear. We want to introduce the value 0 there. We want to switch off the LED. That's it. And exactly the same we are doing. So we will change the value LED, because over and over again we have already changed the value of LED, but our aim is to actually go with the same LED, because we want to switch off from the first LED position, from the 0th LED position, and that is connected to the port number 0, pin number 4. So port number 0, pin number 4, we want to make 0. So that later on is connected to, because that is already connected to the 0th LED position, and the moment you will make that thing as clear or 0, then it will go switch off. It will switch off definitely. So that is the simple program. If you would have understood this program, other programs are easier. I mean, not so easy, but if you would have understood the concept behind controlling the LEDs, other programs, so the logic will differ. Otherwise, everything will remain same. That core and peripheral interaction would remain same, that how core would use the output ports, the output means output port and its pins to actually control the outer peripherals. That is, now I will run this program first. That is Johnson counter, the saving counter. We will now I will include this. Okay, there is no error, no warning. Now I will run the program. Now here you can see in the direction FIO direction register, pin number 4, 5, 6, 7, 8, 9, 10, 11. These pins are set as 1. So that the value 1, that means from system, these are output ports. From that reference, if you would see, these are output ports. And then one by one in FIO set register. So inside this loop, one by one, we are actually setting it. One by one from port number 4, we are setting it. That's it. Then we are clearing it. So setting it, and then we are clearing it, and that is reflected over the pins. So whatever exactly we are doing in FIO set, so FIO set register, so exactly its reflection we can see over the pins. That's all we are doing in this program. So this is the Johnson counter, as you can see, the Johnson counter. So if later on, so already we have created out of linking and compiling out of that. Now we are with our hex file. So if you will download the hex file over to the ROM in Git and then run the program there. So here virtually, as we can see the LED pins and these LEDs. So there you can physically realize the blinking of LEDs, the switching on and going off of the LEDs. So that is corresponding to the simple program which reflects on how to interact with the peripherals from core perspective. Now in the next program, we will understand the reverse Johnson counter. That is exactly the reverse. Here we have numbered the LEDs from left side. And so from left side to how to represent, not from right side. So from my perspective, you would see, and if the kit is right in front of me, so I'm switching on the LEDs from my right hand going towards my left. In the next program, just we'll do the reverse. So just the value of LED we have to change. So you can also think what should be the value of LEDs if you want to reverse this program. So reverse Johnson counter we want to come up with where the LEDs initially should flow on from the left side and it should go till the right end, and then from the left side onwards these things should switch off. So for that purpose, what should be the value of our LED? Otherwise the loop structure, every program structure would remain same. So So here you can see the program corresponding to a reverse Johnson counter. In Johnson counter, we have used the LEDs from right side. Here we want to switch on the LEDs from left side. That's the only difference. So the program structure is almost same, but because we are using the port number 0, pin number 4 to 11, initially we have put 1 over the pin number 4 initially, and then we shifted it to 5th, 6th, 7th, 8th, 9th, and 10th, and then later on at the last 11th pin was right. Now here in this case, our aim is to put 1 over the pin corresponding to 11, and then shift that 1 to 10th, 9th, 8th, 7th, 6th, 5th, and 4th. And finally, we want to switch off the LEDs in the same order. So how we can do it? So just we have to change in the first program the value of LED. That's it. So here you can figure out the value of here LED is this. If you will take this value and check what is the corresponding binary equivalent of it. So here you can see the 11th position is 1. The 11th position is 1, and that we will right shift till this one reaches the 4th bit position, and then we will change the value of LED in our program back to this, and then we will do exactly the same thing, but in the next loop structure, in the next for loop, we will use FIO clear instead of FIO set, because initially we want to set the value 1, and later on the next subsequent phase we want to switch off the LEDs. Now if I will initially link my program, compile it, 0 error, 0 warning. Now I want to run this program for your reference. Now you can see here. So here you can see the cycle. So it is starting from the leftmost side. It is going till the right, and because it is in finite loop. So here you can see the same pattern. That is the reverse way of controlling the same LEDs, but in reverse order. So that's how in any order now we can actually control our LEDs. Our next program is to understand that how we can realize the 8-bit up counter. Our aim is to realize the values over these 8 bits as up counter values. These are 8 LEDs in numbers. Individual LEDs we would correspond as individual bit positions. So 8 LEDs corresponds to 8 bit positions. So our value can go over till 255. So we want to realize that that counter we want to realize, which will start from 0 and till 255, and the moment it reaches 255, once again it should start from 0. So that we want to see, it's very simple. As you can see here, I will now show you the 8-bit up counter. It is simplest program, 8-bit counter. We are using the same port. The port number is 0, pin number 4 to 11. So this is the configuration corresponding to that pin select 0. Then we want to set the direction, obviously, so that direction we will see from system perspective, because system will put values over these pins. So those pins which we have configured as GPIO pins are output pins. So here from port number G, I mean, for pin number 0 to 11, it is FF. The direction is 1, set as 1, that means the output direction. Now in the program, so we want to represent the value 1 till 255. So this is the for loop for that purpose, because we want to represent that value, because that's the maximum possible. So already 0, 0 is there, because if nothing is there over the LEDs, every LED uh, is switched off. So at that point, it is representing the value 0. So later on, we want to move to 1, then 2, then 3, then 4, then 5. We want to go till 255 value. So I less than 256. And what exactly we want to represent there? So that is the C is equal to 0. Initially, the C is equal to 0. So LPC GPIO 0, FIO pin is equal to C, whatever be the value of C. So initially the value of C is 0, and in the next subsequent, because we are incrementing C, so next time it is 1, then 2, then 3, then 4, then 5, then 5, and it will go till 255. So the value over the LEDs would go from value 0 to 255, because it is less than 256. But whatever be the value C, at that point we will latch shift it by 4. Why exactly we are doing it? Why are we doing it? Because we are using the port number 0, pin number 4. But the value of C, the representation of C is from the 0th position. So directly, if you will put values over FIO pin, so you will not be able to hold those values, which is the equivalent binary of C over the pin number 4 to 11, because whatever be the C, its equivalent 8 bits should overlap over the position of the pin number 4 to 11. Then only because then these pins are connected to LED pins, then you will get the correct representation of that binary value of C over the LEDs, because LEDs are connected to port number 0, but from pin number 4 to 11. So whatever be the C value, because that position is starting from 0, that's the binary value. Over the FIO pin, if you will directly give the value, then it will start from the 0th position, then you will not get the correct representation from 4 to 11. So whatever be the equivalent binary, that equivalent binary we have to overlap over the position in FIO pin 4 to 11 bit positions. So that's why here we have shifted it 4 times. That shifted it 4 times, then this is just the delay in between, so that we can see the result over our LEDs for certain duration. That result would still be there for certain time to realize, and then we will increment the value, and in the same way loop we will go and increment it. So if we will run this program, so now I will run this program for your better understanding. 8-bit counter. After compiling, so building target one. So after its compilation, I'm running it. Peripherals. So here you can nicely see over the pins. This is up counter. This will go till 255. So here, once the value reaches 255, because here in this loop, once the value reaches 255, we're not making any adjustment because this loop will not change the value of C. So here, to actually change the value of C, once one more if condition you may require, if the value of C is beyond 255, at that time you can once again make the value 0. So that change you can do, because here what this program exactly will do, this program will go in one cycle only, then because the C will keep on incrementing. So that's it, because here you are not making any changes to C once this value of C reaches 255. So this loop will always be in cycle of 255s, but initially your value of C will reach as 255, and it will go beyond that. So later on you will not get the nice representation of those values because the C value is not correct. So some changes this program require that you can see. So that is all about the binary up counter. Same way you can start the C with 255, and then you can keep on decrementing that value. That corresponds to down counter. Once the value reaches 0, once again you can make the C 255, and in this way you could have the nice down counter. So up counter, down counter. So next one is ring counter. I want to show you, I mean, just if you know the ring counter, you can easily now write the code corresponding to controlling the LEDs for representing ring counter values. What is the ring counter? So we have 8 LEDs in place starting from right side 0th position till the 7th position. So initially we will blink on, or means we will switch on the LED 0. We will switch it off after a while, then we will switch on the first, we will switch it off, then we will switch on the second, third, fourth, fifth, sixth, seventh. The moment you reach a 7th, you will switch on it first, then you will switch it off, and then you will come back. So you will completely make the ring. So means you will complete the ring. So that process of making ring makes it a ring counter. you will do it? It is simply means you have to play with the pin values. So we are exactly using the same pins, pin number 4 to pin number 11 of port number 0 exactly. So these two lines will remain same because these things are configuring initially those pins as GPIO pins and then later on setting their direction as output direction. And here the value of LED is 1. In fourth position is 1 because that is where you want to switch on the LED. So corresponding to that bit position, because pin number 4 is connected to the LED position 0. So that's why LED is has the value this. Now in this for loop, you will go inside this for loop 4 times. The moment you will go inside this loop, so what exactly you will do first? First you will set the value. So first you will switch on the LED. So corresponding to switch on, you will FIO set LED. Then you will introduce the delay. You will then remove that value. You will switch off the value. To remove that value, FIO clear register you will use. There you will set that bit position as 1. And then because now the next move would be towards the next one. That's all you will do. So LED is equal to 1. And after completing this loop, once again when you will go inside the infinite loop, LED value you will notice would start from its original value. That means from the 4th bit position. Then once again you want to set it as 1. Now I will include to ring counter and will show you. So here, as you can see, the ring counter 1, 2, 3, 4, 5, 6, 7, and then once again same. So it is repeating and giving you an impression of forming a ring. So ring counter is over. Now we'll go to one program where we'll understand now the input pin. So how you can use input pin, because whatever we have understood so far, there we always used output pins. So those port always been configured their pins as output pins. Now somewhere suppose our idea is to utilize any pin as input pin, and that our system would constantly monitor. The moment that value becomes 1, then our system will produce certain output. So then our system will do something. So here in up down counter, as you can see, here we will connect our external switch. So there is one external switch which we will connect to one particular pin. That pin we will configure as input pin. Our system would constantly monitor that. We will ensure through writing code that our system would constantly there monitor. The moment that value become 1, means the moment you will press that switch and that value will go over to that pin, then our system will either increment the value of C that we will then later on display over LEDs, or depending on if you will not press the switch, then it will decrement the value, then it will be as the down counter. So here in the same program, up and down counter based on our external switch configuration. The moment we will press switch, it will take you to up counter, it will increment the values or decrement the values depending on the code we will see. But in the same program, it depends on the value over the input pin which is connected to external switch. So here exactly the same pins we are using to control our LEDs. So pin number 4 to 11 of the port number 0. So for that purpose, these two lines are exactly same because we are using the port number 0, pin number 4 to 11. those pins are output pins. So these two lines are exactly same. But here we require one more external pin. That pin we are using the port number 2, pin number 12. Any pin you can use. If you will use some other pin, then the port will slightly change, because there it should have the reflection of which pin you will use. Here I'm using the port number 2, pin number 12. So port number 2, pin number 12 I'm using. Corresponding to that, you can check. For that purpose, we have to use the pin select 4 register. So pin select 4 register we have to configure in this manner. So here I want to show you the value. So pin number 12. So 12 to the 24. So 24th and 25th bit should be 00. So now I will take this value and I will go and write the hex value here. Now you can see here, if you will notice, 1 2 3 4 5 6 6 is the 24. So 24th and 25th position is 00. That means that's way you can explicitly configure the pin number 12 of port number 2 as GPIO pin. Then in LPC GPIO2, so now already, as we have discussed, 5 registers are there through which you can monitor, through which you can handle your port. So here we have to handle the direction. So FIO direction of the port number 2 we will use, and we are setting the value 0. So every value will become 0. That means that pin port number 2, pin number 12 will be used as input pin. So here in the code, what are we doing? So we are checking the pin if LPC GPIO 0 FIO pin. So FIO pin, as you know, will give you all 32 bits. All 32 bits corresponding to all 32 pins of port number 2. Now we are only interested in pin number 12. So pin number 12 corresponds to, if you have to just notice the pin number 12 value. So in FIO pin, the 12th bit position, if you will count or start your counting from the 0th position, then the 12th bit position will give us the value corresponding to the pin 12 of port number 2. And that we will end with 1 left shift by 12. So if that value would be 1, then we will go inside this value and then we will decrement our C. So here we are using the switch for two purposes. If we will press the switch and the value is 1, then later on, so we will go inside this loop and then we will decrement whatever be the value. Initially we are using the value C, but whatever be the value of C, that it will decrement. So once you will enter inside this if condition, if this if condition is okay, since you have already pressed, then it corresponds to down counter. Otherwise, it corresponds to, if you're not pressing the switch, then it is C++. Now it depends on two parameters. Sometimes even if you will press the switch, instead of putting value 0, the value over, it depends on whether level 0 or level 1 is there in your kit. So depending on that, we have to see that it may be possible that if you will press the switch over the pin, the value would be 0. So in that situation, you will not go inside at that time. I am considering where if you will press the switch, the value over the pin would be 1. In that situation, you will go inside the loop and then it will act as down counter, otherwise it will act as up counter. Now we will check the extreme conditions. So the extreme condition could be, the C could be -1, because the moment you reaches 0, at that time if you will press the switch, the value may be -1. So at that time, because -1 is now representation over the LEDs, so at that time we will make the value with C is equal to 255, because that time 0, so back to 255 as a ring counter. So we want to represent at that time 255. So how to represent it? Very simple. Over the pins, just put the value C, but directly you can't put the value C, because your pin starts from the 4th bit position. So you have to shift that value by 4, left shift by 4, then that will go over the pin number, port number 0, pin number 4. Those are already connected to LEDs, and you will get the nice representation of that in binaries. Now the next condition is if your value is if your value is 256. So because the right extreme is if the value is 256, at that time you want to represent 0. So at that time the next value is not 257, because over the 8 LEDs you can't represent 257 or 256. At that time the next represented value would be 0. So that we are doing. So these statements corresponds to consider or tackle the extreme value, and this is to nicely represent that over our LEDs. And here we are introducing the delay. So this was all about controlling the LEDs. In our next video, we will take some other peripheral and see how our system or code can interact with that peripheral, can control that peripheral. So hope you must have enjoyed this part of study, and we'll see you with some other peripherals.